Okay, question A. This is a probability Venn diagram question. So we've been given three events, A, B and C, and we've been given quite a few of the probabilities of the various combinations of events happening. There are three variables that we don't know the answer to. We've got an X, a Y and a Z that we've been asked to calculate. We've been given a couple of bits of information. We've been told that the events B and C are mutually exclusive. It's going to be useful. And we've also been told that A and C are independent. So we need to use our knowledge of our probabilities to be able to calculate our values of X, Y and Z. First of all, let's start off with this one. So B and C mutually exclusive. So these two events can't occur at the same time, which means there's going to be no overlap. So we've already got a Z in the three-way overlap, but my value of X must also be 0. So B and C mutually exclusive. This implies that X is equal to 0, and I've just got myself my first accuracy mark. Next bit of information we've been given, which is A and C are independent. So that means that the probability of A times the probability of C is going to be equal to the probability that A and C occur at the same time. So probability of A, and this is where we need to be careful, probability of A occurring isn't just this 0.1 over here, it's all of the possible combinations that are included within my event A. So it's 0.1 plus Y plus Z. 0.1 plus Y plus Z. And I'm going to multiply that by the probability that C occurs. Probability that C occurs is my 0.39 plus my Z plus 0 plus my X, which, well, I know that's 0 as well, so I'm not going to bother writing that down. So 0.39 plus Z. And that's going to be equal to the probability that A and C occur at the same time. Well, that's my intersection between A and C. I know that three-way split is 0, so this is going to be my probability Z. So far I've got an equation. I've got two variables. I've got Y and Z. I've got some numbers. Can't solve that as it is on its own, but I'm going to number it up. Equation number 1. There's one other piece of information that has been implied by the questions. It's not stated specifically, but I've got a Venn diagram. I know that means that the probabilities in that diagram must add up to 1. So the sum of my probabilities equals 1. Or what have we got? So we've got 0.1 plus 0.3 plus 0.39 plus my 0.06. Don't forget, we've got this is the probability that none of the three events happen. I need to include that as well. That's part of my 1. So I add those numbers. I've got my variables. X I need to put in, but remember it's 0, so I don't need to write it. Plus Y plus Z. So plus Y plus Z, and that's all equal to 1. Well, I've got 0.4, 0.79, 0.85. So 0.85 plus Y plus Z is equal to 1. So my Y plus Z is equal to 0.15. I'm going to number that up, number 2. Well, Y plus Z, I've got this as an actual term in here, so I could rearrange this and substitute it into Z. But I'm just going to substitute Y plus Z into here. So this is going to give me 0.1 plus my 0.15. So what am I doing? I'm subbing 2 into 1. So 0.1 plus my Y plus Z, which was 0.15, times 0.39 plus Z is equal to Z. This is 0.25 times my 0.39 plus Z equals Z. Multiply both sides through by 4. We've got 0.39 plus Z is equal to, oh, that's supposed to be a Z, is equal to 4 lots of Z. So 3Z is equal to 0.39, or just running out of space. Z equals 0.13, which means that my Y value has got to be equal to 0.02. So there were a couple of method marks available. So using the fact that sum of my probability is equal to 1 gives me a method mark. Using the fact that A and C are independent also gave me a method mark. But I needed to accurately identify what I meant by each of these three. So just writing this top line down in the mark scheme didn't give me any marks. I needed to have identified that this is 0.1 plus y plus z, and probability of C was 0.39 plus z, and this combined probability was z. So if I got those, I got a method mark, and then I got a couple of accuracy marks for my value of y and z at the end. Okay, question 9, final question. This is a hypothesis testing question, and we've been given some information. We've been told 15% of customers buy chocolate. Let's highlight some of the information we've been given. So 15% buy chocolate. Shopkeeper believes that if they move chocolate closer to the till, that his sales of chocolate are going to go up. And he's done a sample of 30 customers, and he's found that 8 of them have bought chocolate. And he wants to test his idea that by moving them, he's actually improved his sales of chocolate. So Julie's had a go at the question, and she's made a couple of mistakes. And part A, they've asked us to identify the 2 errors that she's made. So the eagle-eyed amongst us spotted that if the null hypothesis is P equals 0.15, that 15% historically that bought chocolate, that the alternative hypothesis, H1, can't include the value of P equals 0.15. So this P greater than 0 and equal to 1.5 is wrong. It needs to be P greater than 0.1, strictly greater than, and not greater than or equal to. So first mistake. Second mistake, well, first of all, she did the next bit right. She identified that X was going to follow a binomial distribution with 30 trials. That was the 30 customers with probability 0.15. That was the 0.15 from the null hypothesis. So that bit's correct, and we like that. Let's give that a tick. But then she's gone to say the probability that X equals 8 equals this 0.0420. This is less than her significance level of 5%, 0.05, so she's going to reject H0. But the mistake she's made, she's testing just that it equals to 8, and she needs to test it out against the probability that X is greater than or equal to 8. So 2 mistakes. She's included the equal to 0.15 as well as strictly greater than, and down here she's just equal 8, and she needs to be looking at the probability that X is greater than or equal to 8. So that's part A. Part B, explain whether or not these errors will impacted her conclusion that she was able to reject the null hypothesis. So probability that X is greater than or equal to 8, we know that's the same as 1 minus the probability that X is less than or equal to 7. So bigger than or equal to 8, less than or equal to 7, no overlap, so they must add up to my value of 1. We can work that out from our calculator, so especially if it's switched on. Our value of X, we're looking for 7. Number of trials we've got is 30. And our probability of success is 0.15. And that's going to give me a value of 0.9302. So 1 minus that, if I did that somewhere earlier, is 0.0698. So what she got? So rather than having a number that's smaller than her 5%, she's actually got a number that's bigger than her 5%. So write that down. It's bigger than 0.05. So will they have affected her conclusion? Yes, they will. So she cannot reject H0 because this result is around about 7% likelihood of success. So it would happen every 7% at times. So it's outside her 5% significance level. She hasn't got enough evidence to reject H0. In the third part of the question, we've been asked to calculate the critical region for a one-tailed test. So we're just going to be considering the probabilities that are greater than 0.15. So one-tailed test of the shopkeeper's belief. Probability of the tail should be less than 5%. So we've been told significance level needs to be at 5%. The one we calculated in part B, we calculated the probability that x was greater than or equal to 8, 0.0698. So we're actually quite close to that 5%. So I'm going to have a look at the probability that x is greater than or equal to 9, and I'm looking for the first result that is going to have a significance level of less than 5%. So the probability that x is greater than or equal to 9 is equal to 1 minus the probability x is less than or equal to 8. So that less than or equal to 8 or greater than or equal to 9, I've got all my possibilities, so it must add up to 1. I can put that into my calculator. So it's currently set on 7, so if I change that to an 8, my n's still on 30 tests, 30 trials, and my p still set at 0.15, so that's all good. I can hit that, and that's going to give me 1 minus 0.972, which is equal to 0.0278. So 0.0278. This is less than 5%. So this is a significant result. So x greater than or equal to 9 is the first value that's in my critical region. X is greater than or equal to 10, and this number would start getting smaller and smaller and smaller, so that would also be in the critical region. X greater than or equal to 11, again, this number here is going to get smaller and smaller, definitely less than 5%, definitely in my critical region. So my critical region is going to be the values of x greater than or equal to 9. So if I got 9 or more customers buying chocolate out of 30, I would have a confidence level of less than 5%, and I'd be able to reject my null hypothesis with that 5% confidence level. So my critical region, which was part C, so the probability calculation, the critical region for this, so the critical region is x greater than or equal to 9, because my critical region. And then part D, we've actually done all the work for already. So part D says find the actual significance level of this test. Actual significance level of this test is 0.278. So it's the probability x was greater than or equal to 9. So we worked out it was less than 5. That was my theoretical confidence level. The actual confidence level that I would get if I got 9 or more customers would be 0.0278. So my actual significance level equals 0.0278. You've still got to write that down. So even if you calculated that within part C, you've got to write it down so that you're recognising that that's your actual significance level. So it's not enough for me to see it on your paper somewhere. I've got to see you actually state your actual significance level is that number 0.278. So no more calcs required, but you do need to recognise that this is your actual significance level of this test. Okay.